Okay, a whole bunch of foundational skills that are coming up in Unit 1 of Pathway 2 in 8th grade. This is going to be the new academic vocabulary that you're going to be seeing. And it's not really even that new: an irrational number, scientific notation, square root. There's some other stuff that we're going to cover. Basically, everything we covered today was all these vocabulary words and every single one of these TEKs that are going to be covered in your class. So the thing that we're going to talk about is estimating square roots that are less than or equal to 225. So that's 15 squared. So you're going to need to know all your squares, your perfect squares from 1 all the way to 15, which is not hard to do. And then we're going to talk about the real number system to review that vocabulary, and then we're going to break down scientific notation. Based on the feedback I got today, we are going to be working on solving, comparing, converting, and ordering rational numbers and irrational numbers next time. So that's going to be the deep dive for this unit. So estimating square roots. Whenever we're talking about squares, we're also talking about, the shape. And we know that squares are the same on all sides. But that's what makes square units whenever we're talking about area. So a square root is just undoing a square. So whenever we have the area of a square, it's going to be 25 square units. To undo 25, it's what number was multiplied by itself to get 25. That looks like this, the square root of 25. So you can do a practical guess and check by doing, okay, well, what's 1 times 1? What's 2 times 2? What's 3 times 3? What's 4 times 4? What's 5 times 5? Oh, dang, there it is, 5. Square root of 25 is 5. Roots in general are just a way to find out what makes squares and cubes. So a cubic root would look like this, okay? And that would, let's say, the cubic root of 8. That means you have 3 dimensions of a cube, which makes it a cube, and you have a number times a number times a number. You could do the same exact process you do with square roots, which would be what's 1 times 1 times 1. Cool. 2 times 2 times 2. There it is. That number is 2. 3 dimensions by 2 makes a 8 cubic unit cube. So whenever we're talking about square roots, think about what number times itself makes that number. Anytime you want to square a number, like 5 squared, you'll get 25. To undo it, you do the square root. That vocabulary is important. So what about if you don't know and it's not a perfect square? Well, if it's not a perfect square, then you can estimate square roots. So let's go with like 30. There is no whole number times itself that equals 30. But we do know perfect squares that are before 30 and after 30. So going through the process again, 1 times 1, 1. 2 times 2, 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. Wow, that's really close. Okay, so we could do 25, and that is going to be 5. We want that, okay? Now we're estimating on a number line. So that means the next one above it is going to be 6. And that would be the square root of 36. Okay? In between is going to be 5.5. That makes sense because in between 5 and 6 is 5.5. Now the next question we have to ask ourselves is, what's it closer to? 25 or is it closer to 36? It's almost right in the middle. So it's 5 away from 25 and 6 away from 36. So it's slightly closer to 25. That means that it's going to be a little bit below the halfway mark. So we're not looking for exact answers. What we're looking for here is estimations. So we could say a 5.4, and that would be okay. We're trying to come up with a reasonable answer to estimate a square root. So we know it's less than 5.5 and it's almost smack dab in the middle. So this is a very reasonable answer. Now, if we wanted to look at another one, we could do, say, 90. Going all the way through the squares, the square root that I could think of that's beneath 90 would be 81. And that's 9. 9 times 9 is 81. That means the one above it's going to be 10, which is the square root of 100. In between 9 and 10 is 9.5. All right, now let's determine what it's closer to. It's 9 away from 81, and it's 10 away from 100. Again, it's barely below the halfway mark. So it's closer to 81 just by a smidge. Just to estimate, we'd say about 9.4. You're not looking for an exact answer. You're looking for a reasonable answer. An unreasonable answer would be to square 90 and get 8,100 and say that that is the square root of 90. That's completely unreasonable. It doesn't fit between 9 and 10. Another unreasonable answer would be 9.9. It's not closer to 100. That's an unreasonable answer. So the only reason we're doing this is to estimate with square roots. You can do the same thing with cube roots. You got to know this vocabulary for rational numbers. Natural numbers are also called counting numbers. Okay? Natural numbers and counting numbers are like your caveman numbers. They only would be able to count the things that you can see. If you have 5 rocks, then you'd be counting 5. If you didn't have any rocks, you wouldn't say 0. You'd say, I don't have any rocks. So that's natural numbers and counting numbers do not include 0. Okay? No 0. Whole numbers are where it steps up from there. And you can talk about, I have this amount of rocks. Like if you don't have any rocks, you can say, I have 0 rocks. This has 0. So it's all of your counting stuff with natural numbers and counting numbers, but it also includes 0. To step up from there, integers are all whole numbers, natural numbers, and counting numbers with 0 and all their opposites. So imagine every whole number, 1, 2, 3, 4, 5, all of its opposites, -1, -2, -3, -4, -5, and the thing that separates them is 0. Positive on that side, negative on this side, 0 in the middle. Rational numbers are anything that repeats and or can be written as a fraction or a decimal. Examples. 1/2. That can be written as a fraction. It can be converted into a decimal. What about repeating decimals? Cool. Let's do 1/3. 1/3 turns into 0.33 repeating, right? So it repeats. It has a pattern, which makes it rational. Let's talk about something that's irrational. Pi. Pi is 3.1415 on and on and on and on and on and on. It doesn't repeat and it never stops. That's irrational. If you're sitting there looking at a number going like, this just doesn't make sense, think of it like a person that doesn't make sense. They're irrational, okay? Any other type of thing that's not a perfect square, like the square root of 5, that's not a perfect square. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So that's going to end up having a decimal with a whole bunch of numbers after it. It's not going to be in a pattern. Those are irrational numbers. So pi and the square root of non-perfect squares. So just to review again, counting and natural, no 0. Okay? Whole number has 0. So we're still not talking about any fractions or decimals. Integers, still not talking about any fractions or decimals. Positives, negatives, has 0. Rational, ratio, that's where you start getting into parts. So you could have -2.5, or write that as -2.5. And that's still a rational number, but it's not an integer because it has a decimal or a fraction. Irrational numbers are whenever you have a non-terminating, means it doesn't stop, and it does not repeat. No repeat. A majority of the time, you're going to have rational numbers. This entire system is called the real number system. Scientific notation, just some tidbits, and this is going to be a thing that we're going to work on next time. Big numbers use positive exponents. For example, 5,280. There's always going to be used as a base 10. So always look at the decimal. If you don't see it, it's always at the end, okay? So we know that's always going to be times 10. You know, we're always going to have a exponent. The number that's multiplied by 10 always has to be between 1 and 10. So basically, you could take the first number and put the decimal behind it on every single thing that you're doing. 1, 2, 3. That turns into 5.280, and I moved it 3 times. Positive numbers, like a positive exponent, will tell you to move in that direction. And that's exactly what you would do with this 3. You'd move it 1, 2, 3, then you're back to 5,280. Okay, so the next part is talking about small numbers. So what if you had 0.00023? Well, you know you're going to have something times 10. And we know that small itty-bitty numbers have a negative exponent. You could pick the first number that's not 0, which is 2, and put the decimal behind it. 1, 2, 3, 4. Okay. Now we have 2.3 times 10 to the negative 4th. To work that backwards, because we know that negative numbers go to the left on a number line, we could go 1, 2, 3, 4. That's going to give you, in these blanks, 0, 0, 0, 2, 3, right back to where we started. This is just a way to show really small numbers or really big numbers. And you can see this on a calculator. If you multiply some really big numbers or really small numbers together, it'll come up with an e and then an exponent, whether it be positive or negative. It's something to play around with, and this is going to be something that we continue to work on.